Let's continue on part 3 of our discussion into simple linear regression models. Before we were talking about the relationship between tweet rate and movie revenues. So let's just kind of summarize, before we do the estimations, what we know so far, right? So we've talked about a population regression model. Okay, population means it's going to be Greek letters representing the parameters. Model means there's going to be an error term. So that is yi, which I won't call yi because we have a value. Let's call it revenue with little I. Right? Beta 0 plus beta 1 times by tweet rate I plus epsilon. So we have a context to this particular model. There is a model we want to estimate, and so we're going to keep that context. We have we'll have a population regression line, and that's just the expected value of revenue is equal to beta 0 plus beta 1 times by the tweet rate as well. Again, no error. Now we can also talk about population regression a sample regression model, a sample regression line, but those require estimates, and that's essentially where we're sitting at now. Now we're going to do some estimation. Our estimation tool is Excel. Now, Excel was not designed for statistics. Okay, it's kind of a glue-on. It was mostly meant for accountants, and then they sort of pasted the stat stuff on there. So not optimally designed for regression, but we're going to use it for regression because it is a software platform or software program that you will see in the workplace and is very prevalent. Almost everybody's got Excel right now. Some of the tools that we'll use in Excel, you could also extend this to Google Sheets and Libra and other open source like spreadsheet programs. Okay, so once you know the basics of these tools, the basic fundamental blocks are with every program. It's just looking for them, just knowing what to look for, and that's why we want to avoid being too application specific because this is not a training course, this is an education course, and so we want to maintain that flexibility that I know the key components I need in order to do a regression. Where are they in this particular program? They may be different in this other program. So for instance, if you use R and you would move into R, there are graphical user interfaces for R that make it a little bit more friendly, but you know what to look for. And you know the key statistics that you want, you know how to select them and which ones are important and which ones may not be important in your particular context. Okay, so let's do our estimation. And so we open up our regression and we see it go into Excel and data analysis, and we pick regression. The input, so we select the cells which contain the dependent variable y. We select the cells that contain the independent variable x. When we move into multiple linear regression, all the x's have to be together. Can't be in different locations. This is an Excel thing. If you use a stats package like SPSS or Minitab or R, it doesn't care. You can select from a menu of potential variables, and they don't all have to be contiguous. Excel requires them all to be contiguous. Always great to have labels at the very, very first row, just so that when you get the output, you know it makes sense as to what is referring to what. Otherwise, it'll be a goo of numbers, and it makes interpretation for you, interpretation for your client, very difficult. Confidence level, you can have that or not have that, depends on the situation. We avoid the constant as 0. There are certain theoretical reasons why we need to have a constant in our linear regression. And it, lack of a constant can lead to odd results in our what we call our R-squared, or our coefficient of determination, and it just creates potential pitfalls unless there's a really, really, really compelling reason that you need that constant to be zero. We stay away from that box, and for the most part, we stay away from the box. Okay. We're going to select the output range, where you want that data to go to. Sometimes you want it in a new worksheet. Sometimes you want it in a new workbook. Whatever the case may be. Now remember, we were talking about those errors, right? Residuals, errors, and so there's all sorts of choices for residuals. And having the residuals, calculating residual plots, that can be very useful. And later on in this course, we will use those residual plots and those residuals to diagnose any potential problem areas in our models. That's going to be very useful later on. Normal probability plots, we'll talk a bit about those more in the multiple linear regression, but those have an important place here as well. One of our assumptions, which we haven't gotten to our assumptions yet, but one of our 4 assumptions is that the errors are normally distributed. Normal probability plot is a very nice, simple tool to check to see if that is so. There are tests for normality. Won't get into them in this course, but understand that there are tests, and then you can look them up later. But for now, we'll just focus in on the normal probability plots. But that's more in the future. Okay, so we have our dialog box, and they'll show you how to use this in the lab as well. But it doesn't hurt to get a couple of perspectives on this thing. So we get our output, right? And here is our line. Here is our results. Now, we sort of start off with a bunch of measures at the very top that are very useful to us, related to the regression statistics, which we'll talk about in a few moments. We have this ANOVA table here. Again, the key area for statistical testing. The regression statistics, a key area for evaluating the goodness of our model. Right now, all we sort of know is things related to estimates and the line. And so that's what we have here. These coefficients really describe the line. So when I, for instance, consider the sample regression model, right? That's just telling me that the expected value for revenue equals to, now because it's a, excuse my handwriting here, sample, we have values. What's our intercept? Well, I look at the coefficient for intercept, and I get 1.15 plus my estimate for the slope, and then tweet rate, and because it's an error, plus E. So expected value, my bad. No error in expected value. That should be line. Bing. Sample regression model, yikes, would be revenue equals to 1.15, the actual estimate, plus 0.079, and then the tweet rate, that I plus an error. Okay. Now note, we could easily have gone revenue hat for that expected value for the line as well. And hat's a nice sleeker way to represent it. I like the hat, but expected value, it means the same thing. The key thing is now we have our coefficients, we have actual estimates. Now we have a couple other items with the model, right? We have coefficients, we have the error for those coefficients, we have some t-stats, right? We've done some t-statistics before. Look, we got some p-values, right? We see t-stats and p-values flowing together. We're suspecting there's a statistical test in behind the scenes. There is, and we'll be doing them, so that's very cool. Sometimes on the Excel, 3 decimal spots, if you have a very, very small p-value, it rounds to 0, but it's not actually 0. So just be aware of that. We never, ever say that the p-value is 0. Never, ever. Never, 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 never. It can be close to 0, but it's never actually 0. It can approximate 0, fine, but never equal to 0. Okay. So there's our output that we know about, right? A couple other pieces of information there that we will soon discover, but this is the important stuff that we're acquainted with right now. In R, you'll see the same kind of information. You'll see, so for instance, the coefficients. There's our estimate for the intercept. There's our estimate for the slope. There's the standard errors. There's the t-stats right there. There's the p-value. Okay. Don't read too much into the 2.2 to the e to the minus 9. I mean, it just means it's really small. So for instance, R will give you a little bit more decimal spots, I guess you would say. Right? So notice how they did not round it to 0. There's some measures that we have here. Rsquared being the important ones for us. There's this F statistic, which was in the ANOVA table that we had before. So much of the same material, same information on one versus the other, just expressed slightly differently, and the formatting is a little bit different. Okay, but same basic information, and this is why it's so important to know what that basic information is, so that we can look at any output from any stats package and understand what the heck is going on. Okay, so we already did that. So now we make predictions, right? Predictions, that's the whole point of what we're doing. So if the tweet rate is 500 per hour, what is the movie's expected revenue? Okay, so what is that expected revenue? Well, all we do is we just plug in stuff in. 1.15 plus 0.7079 times by the 500. That's it. That's it. We've made a prediction. And that's one of the big deliverables in this whole process is we make predictions. People, our client wants to know what the future holds. What's going to happen? What can I expect if this scenario occurs? And in this case, what you can expect is to have revenues of about $40.65 million. Making predictions, just plug in proposed values. We don't need to make it more complicated than it is. Now, here's the important stuff. Really, really important stuff. All of it's important, but this is important too. This thing called the coefficient of determination. The coefficient of determination has an alias. Sometimes we call it our good friend the R-squared. Okay. It is, and this is key boilerplate language we need to really focus in on, it is the percentage or proportion of the variation in Y that is explained by the model. Y changes. Our dependent variable changes. The whole point of the model is to try to predict or try to explain what is driving that change. What is causing that change? So the purpose of our model is to try to explain what causes or what's driving changes in our dependent variable, our Y. We bring in independent variables to help explain those changes in Y. Y does change. Right? Not all movie revenues are the same for every movie. Right? That makes sense. Why? Our question is, why are they different for different movies? Well, then we have a model. Right? We have a variety of independent variables that we think explains why different movies earn or different amounts or have different amounts of revenues. How good we do is the R-squared, which is also called a big league coefficient of determination. So usually you don't see, hey, what's the R-squared on that? Now, what's the coefficient of determination? Or discuss the goodness of fit. It could be even vaguer than that. Okay, so again, that R-squared, the coefficient of determination, is the percentage or proportion of the variation in y, whatever that y is. So in this case, it would be the proportion of variation in movie revenue that is explained by this model. Another estimate for goodness of fit, how well our model is at describing the data, is the standard error of the regression line. It's also called the standard error of the estimate. It is essentially the average distance from a given observation to the line. It's like a standard deviation. Okay, so it's like the average distance between a given any given observation. So average distance from the observations deviate from the line. A smaller number is preferred to a larger number. It's really hard to get a wrap onto what's a small number, what's a large number. It really depends on the scale of the numbers involved. So it's harder to interpret than, let's say, the R-squared. R-squared is easy to interpret, right? Percentages, it's like your grade. Higher percentage is preferred to a lower percentage. Right? It works. Scaling is not an issue because 99% in one case and 99% in another case. Now, what can be a little tricky with the R-squared is certain models will have more randomness to them just by the nature of that particular model. And so there could be, you could get a R-squared of 52% in one case, and that's a great model, get an R-squared of 75% in another case, measuring a different X and Y variables, and it's not so good. So it sometimes, higher R-squareds is better than lower R-squareds, but when you're starting to compare across models and across different Ys that we're trying to predict, it's harder to say that this R-squared is better than that R-squared. But the generality is that higher R-squared is better than lower R-squared. Lower standard error of the regression line or standard error of the estimate is preferred to higher ones. We like the R-squared better because it has a little bit better intuitive understanding, and all sorts of stakeholders can understand percentages and proportions, even though a standard error of the estimate might be something that's a little clunkier to really express. Okay, so we'll just go into what's going on here behind the scenes when we start to calculate this R-squared, or what's driving the calculation of R-squared. So we have variability that's explained. Right? Our model explains a certain amount of variability in Y. And this is often referred to as the sum of squared regression, or SSR. Sum of squared regression, or SSR. And that's how much our regression explains. And then there's that unexplained stuff, right? Sum of squares, error, SSE. And so there's our two components. It's a world of two things we can explain, things we can't explain. It's kind of a simple world, isn't it? I can explain this much, I can explain this, I can't explain that. Okay? Together represents everything, because it's a binary world. Right? So sum of squared total is SSR plus SSE. It sort of makes intuitive sense, right? Things we can explain, things we can't explain, together is everything. So nothing complicated there. And now we grade, right? It's like a test, right? 10 questions, you got 8 right. That means 8 of them you were able to explain, 2 of them you weren't. 8 plus 2, there's the whole test. Right? So now we're starting to calculate our R-squared. How did we do? Well, take the 8 we could explain, divided by the 10 questions, 80%. Boom, right? Done. Bob's your uncle. It is as easy as that. I mean, a little bit more math. We'll see a couple of equations here. We can gain an appreciation for there's maybe a little bit more behind the scenes, but its essence is that. Right? We got what we could explain out of a variation that we could explain out of the total variation. That's our R-squared. That's our coefficient of determination. That's a measure of the goodness of fit for our model. And so now let's look at our R-squared here. Now in this simple linear regression case, simple linear regression, SLR, we just want to focus in on old-fashioned R-squared. Okay? And in this case, the coefficient of determination, R-squared, is equal to 0.8242. Let's go with just 4 decimal spots. We see that up in our output. Now, there's lots of other items in the output. Right? Multiple R, we're not going to worry about at all. Adjusted R squared, we will worry about in the multiple linear regression case. So what does that tell us? This tells us that 82.42% of the variation in movie revenue is explained by our model. There you go. Burn that into your head. So that's actually a pretty high percentage, right? When you can think of all the other things that could be happening. Of course, it means that 18% of the variation movie revenue our model's not even touching. But it's something, right? We also have the standard error of the estimate. Okay, so sometimes we call it S little e, and that's the standard error of the estimate. And in this case, that just equals to 13.3165, let's say. Okay. That one's a little bit trickier to really get a sense for. That's the sort of the average deviation from the line. So when we think of our old days in Management Science 103 or Stat 151, and we were doing confidence intervals with normal distribution, and we were talking about plus or minus 1 standard deviation was some percentage of the observations, plus or minus 2 standard deviations was some percent of the observations. That is essentially the same here. So we can use that little tool, which we call the empirical rule. Okay. And we'll see we'll see our assumptions later. But one of our assumptions is that we have a normal distribution, and so we can these errors, right, standard error of the estimate, follow a normal distribution. And what does that normal distribution say? Well, plus or minus 1 standard deviation, SDV, is about 68% of the observations, right? Plus or minus 2 standard deviations, 95.44% of the observations. Plus or minus 3 standard deviations, it's about 99% of the observations, right? So, depends, right? So what we can say now is plus or minus 13.316, our estimate, right? 68% of the time, plus or minus 2 times 13.3165, about 95% of the time, and so on. So when we think of the context of our $40 million movie, right? So from our previous example where X is equal to 500, right? Our prediction would be 40.65 plus or minus 13.3165, and 68% of the time we'd be in that range. 40.65 plus or minus 2 times 13.3165, and between those two numbers we'd expect to be there about 95% of the time. Right? So we can be looking at 40 million, 41 million plus or minus 26 million, 95% of the time. That's a pretty wide range, right? I mean, for that, in that particular case, that's a pretty wide range. I mean, essentially mean we could be between 14 million and 65 or 66 million. That's a huge range, right? So there's clearly, we kind of suspect the stuff is driving, especially when we get into the relatively lower tweet rates. Okay. R, you'll see the R squared up here. They call it multiple R squared. I know it's everybody's got different names for stuff. It's a little bit confusing. Multiple R here is not the same as the multiple R there. the default is Excel will be the one with the goofier choice. Okay, so if you're faced with a conflict of this versus what you see on Excel, the Rsquared will be the more statistically pure choice. It'll be the safer stats option. Let's put it that way. But we see it. We see it 82.4. We see a standard error. They'll call it the residual standard error, but there it is, right? 13.32. So we just have to understand that sometimes different programs will represent these differently. Just slightly different terms, but if you have an idea of what those terms are representing, you can work with it, and it's easy to make the linkage. Okay, and this comes with practice and experience. Okay, we've done that, so we're all good. We've talked about the standard error of the estimate, a little bit of the notation. That's good. So we sort of have an idea about that. These will be an ongoing theme. Anytime we have output, we will roll through all this stuff over and over and over again. So we will be doing lots of repetition on these particular measures. SSE, now I'm not going to get too far into the weeds on this. This is a mean squared, the mean squared error. And just finding a mean just means we take a summation of something, divide by its degrees of freedom. That's all we've done. Any value of a mean is the summation of something divided by its degrees of freedom. So we have SSE in this case, which is the sum of squared errors, divide by n minus 2, and we get estimate for the standard error of the estimate squared, okay? Which is sometimes called the mean squared error. Mean squared, so it's going to be square and stuff. What's the average squared error? And then that's all this is, okay? And we will see that on our output as well. Okay, so we go back a couple of steps here. We see mean squared of the regression, mean squared of the error right there. Okay, so essentially, if you took this 13.3165 and you squared it, you get 177.3294669. Okay. All right, so we just note that when we start talking about degrees of freedom, they actually do show up in a formula. And perhaps we don't really appreciate that terribly much. So for instance, if we think back to our old days when we were finding variance, right? And we had an xi minus x bar squared divided by n minus 1. Well, when we were doing testing for variance, what was the degrees of freedom? N minus 1, right? So that denominator does have special meaning to us. And in this particular case, as in most cases, it's our degrees of freedom for this particular estimate, which when we get into testing will be very important to us. So again, goodness of fit. We have our two measures that are important to us: standard error of the regression, sometimes called the standard error of the estimate, and the coefficient of determination. Again, the coefficient of determination, percentage of the variation in y, and give y some context. What y are we talking about? Explained by the model. And boilerplate language, maybe not the most eloquent or poetic wording, but delivers the message. That's what's important. Okay, so we've done this one, right? We talked about that. The empirical rule, that's all that slide is going on, and we've discussed this already. Review it. It's a pretty good, gives you a pretty good intuitive for a range of estimates, and a lot of people are interested in, well, what am I looking at? Like, what's a lower bound, upper bound? It's the whole point of why we did confidence intervals. I want to know, I know that it's probably not going to be exactly 40.65 million. What kind of range of possibilities am I looking at? As a business person myself, it's a question I ask a lot, and so it's an important one. Okay, so, and we've pretty much worked our movie tweet rate already, okay? But, always review, you see the numbers, kind of understand where everything is, and you also want to understand where it is fairly quickly. Okay. Now, testing, coming up in the next segment.